Okay, everyone, welcome to the SESE Colloquia. Are there any announcements? No? All right, well, I'm happy to introduce our speaker today, Dr. Marissa Tremblay from Purdue University. Marissa is a noble gas geochronologist with expertise in cosmogenic applications. And so she has her undergrad from Barnard College from Columbia University, and then PhD from UC Berkeley, where she worked also in the Berkeley Geochronology Center. And then she had a couple of postdocs. First one at UC Davis with Sujoy Mukhopadhyay, and then went to Scotland and was at a Royal Society Fellow or Newton International Fellow of the Royal Society. And then went to Purdue, where she's an assistant professor. She's also honorary assistant professor at the University of Wisconsin-Madison, which is interesting. And she's won a number of awards, including most recently the Sloan Research Fellowship and also the Marion Milligan Mason Award for Women in the Chemical Sciences, which is from the American Association for the Advancement of Science. So we're really grateful. Oh, and one more, another nice award I noticed was Doris M. Curtis Outstanding Woman in Science Award from the Geological Society of America. So we're really grateful for your visit. And Marissa's title for her presentation is From the Alps to Outer Space, Advancing Our Understanding of Geologic Processes Using Cosmogenic Noble Gases.
Can you hear me? I sound good on Zoom? Fantastic. Well, thanks everybody for coming and having me here today. It is very nice to leave Indiana in February and come out to Arizona. So I'm super happy to be here. So today I'm going to be talking about cosmogenic noble gases, but I kind of want to step back for a second and tell you that my research group, we work on a really wide and diverse range of problems in geological sciences. So we do a lot of work in landscape evolution and tectonics. Quite recently, I've started working on the evolution of magmatic systems on Earth. And I also have developed some techniques to look at paleoclimate and terrestrial environments. And of course, since I'm here at SESE, I do some work on planetary materials as well. And I have this excellent approach to be able to work on all of these diverse problems, which is that we use noble gases in rocks and minerals to look at the mechanisms and magnitudes and rates of geologic processes. So my lab, we also do a lot of work on radiogenic noble gases, so noble gases produced by radioactive decay. Today, I'm just going to focus on the work that we do with cosmogenic noble gases. And if you don't know what that means, I'm going to explain it to you now. Okay, so this is a department where people use cosmogenic nuclides. So this might be a review for some people. But a cosmogenic nuclide is something that's produced when we have an incoming cosmic ray particle. These ultimately come from supernova events that happen outside of our solar system. And those supernova generate high energy particles that can induce nuclear reactions with other atoms when they interact with them. So this is actually a photographic emulsion plate. There's a scale here on the bottom where you can see one of these nuclear reactions taking place. So there's an incoming high energy particle here at the top, represented by this arrow. And at some point in this emulsion plate, I think this is a silver halide plate, that high energy particle interacts with one of the atoms in that plate, and it generates this spray of stuff that you see tracked in the emulsion plate. Some of these particles that are generated are what we would call secondary cosmic rays that can go on to induce further nuclear reactions. And some of these are nuclides, new nuclides that are produced from these nuclear reactions. And this is what we call a cosmogenic nuclide. So this is a process that happens in our atmosphere. So these primary cosmic ray particles from outer space can interact with atoms, or really the nucleus of atoms present in our atmosphere to generate these cosmogenic nuclides. Carbon-14 or radiocarbon is sort of the most commonly known example of this. And that also generates this cascade of secondary cosmic ray particles that can continue to induce these reactions. And these reactions continue into the Earth's surface and can produce cosmogenic nuclides, what we call in situ, present in rocks that are present at the Earth's surface. But the key thing here is that these reactions don't progress very far when we go from much less dense air into dense rock. And so if we were to look at the production rate of any cosmogenic nuclide in the solid Earth, if we have some surface production rate that we're just calling P naught here, by the time we get on the order of a few meters below the Earth's surface, that production rate in essence goes to zero. So these nuclides are only produced in the upper few most meters of the Earth's surface. And this is incredibly useful if we want to study the rates of surface processes. So I'm not going to spend a lot of time on this cartoon. I just really like this cartoon because these authors have tried to encapsulate all of the different types of surface processes that we can explore using cosmogenic nuclides on Earth. They left this out. We also often measure cosmogenic nuclides in planetary materials as well. So they're really, really useful for looking at rates of surface processes because they're only produced in the Earth's surface. So this table is showing you some of the most commonly used cosmogenic nuclides for studying surface processes. And I'm going to focus on the noble gases today. So I'm going to primarily focus on helium-3 and neon-21, although you'll probably see some data from these other nuclides scattered, buried a little bit in my talk. And the cosmogenic noble gases are really useful for a couple of reasons. One, they're stable. So things like beryllium-10 and carbon-14 and aluminum-26 all have relatively short half-lives, so that limits the time period over which we can use them. They're also relatively easy to measure. Depending on the audience, some people get really mad at me for saying this. So we have some noble gas geochemists in the audience. So when I say relatively easy to measure, we don't have to do a lot of chemistry, and then we don't have to use an accelerator mass spectrometer to measure these nuclides. The process is comparatively simpler for looking at the noble gases. Another advantage is that they have high production rates, particularly in comparison to these radionuclides that we commonly use. So they have much higher production rates, which also helps with the ease of measuring the noble gases. And something that I'll talk about today that has in the past been viewed as a downside, but we actually use this as a positive aspect of noble gases, is that they can experience diffusive loss in minerals, certain minerals at Earth surface temperatures. And we're going to use that to actually look at what past temperatures are like. Okay, so I just wanted to show you briefly here that I have a lab at Purdue where we can make these measurements. This instrument might look familiar to some of you because Kip Hodges has almost the same one in his lab, not quite the same. This end is a little bit different. But I've built a lab at Purdue over the last 2 years while I've been an assistant professor there. And we specialize in measuring the cosmogenic noble gases. And when I was putting this talk together, I found this quite interesting figure that I was like, I just have to share this with people. I think I told Ramon about this earlier. So there was a review paper that came out last year trying to think about what the demographics of people who make cosmogenic nuclide measurements look like. And this is looking at gender. And at the time that they wrote this paper, there were 12 labs with PIs who were women. And then they tried to calculate how long in different parts of the world it would take to get to gender parity in terms of PIs running cosmogenic nuclide labs in terms of gender parity. So North America is way out here. There's some small number statistics problems happening here. But this was really cool because I actually had a conversation with the person who compiled these data, and they included my lab as one of these 12 run by women. And I think that we're the only noble gas lab in this category. So that's pretty cool. Makes us a little bit unique. And before I dive into talking about, so I'm going to go through 3 examples of applications of cosmogenic noble gases that we've been working on. But before I dive in, I just wanted to highlight that I'm going to feature some, but not all of the research that's happening in my group by these amazing people. So I have one postdoc who just joined the group, 3.5 graduate students. I co-advise a student at Wisconsin, which is why I have that honorary appointment, and a group of undergraduates too. Emily Appel, who I put in the center here, is an alumni of this department, and so yeah, so she'll make an appearance a little bit later in the talk. Okay, so I want to walk through 3 examples of applications that we've been working on with cosmogenic noble gases. First, I'm going to take you to the Deccan Traps, which is a large igneous province in India. And we're kind of trying to do something new in deep time relatively for cosmogenic noble gases there. Then I want to talk about much shorter time scale, some environmental work we've been doing, thinking about looking beyond the instrumental record to document snow cover change in the European Alps. And I'll end by talking a little bit about lunar surface temperatures. This is some older work that I've done, but I think it's probably going to be interesting to this audience since we've got a bunch of planetary folks here, and I think I'm getting some static. It's over there. Yeah. Okay. How does this sound? Similar? Okay. All right. So first I want to take you to the Deccan Traps. Okay, I love this cartoon. The Deccan Traps is a large igneous province that erupted across the Cretaceous-Paleogene boundary, and it's exposed today in India. And it's gained a lot of attention in the last few years as sort of being revived as this potential mechanism for what led to the extinction of the non-avian dinosaurs. I will just throw my 2 cents in. I think that the impact event that happened at the Cretaceous-Paleogene boundary is what did the job, but the role of volcanism leading up to that has been something of debate recently. And part of the reason for that is that people have gone back to the Deccan Traps large igneous province. Here you can see the spatial extent of the large igneous province today. It's very big. And they've done the absolute best absolute geochronology that we can possibly do using state-of-the-art technology today to try and better date the lava flows that are present in the Deccan Traps to try and get at how quickly or what the pacing of eruptions were. So there's a lot going on in this figure. All I want to highlight is here's time on the x-axis, and then this is going up through the volcanic stratigraphy. The data in blue are from argon-argon geochronology, and the data in brown are from uranium-lead geochronology. There's a lot here. The thing I want you to notice is that they overlap throughout most of the stratigraphy. Well, there's some differences here, but they overlap throughout most of the stratigraphy. And even doing our best absolute geochronology and applying some sophisticated modeling to try and get timing constraints at even better resolution than the dates themselves, we can't resolve things to better than, say, 50 to 100,000 years using absolute geochronology. And that's just like the limit of these techniques working on these timescales. But when we're thinking about the impacts of large igneous province volcanism on the climate system and then what effect that might have had on life that was on our planet at that time, we need to do much better than 50 to 100,000 years. So this is a figure showing the different sort of range of time scales and duration log scale here of different ways that we can force the climate system. So you can see large igneous provinces here have both long time scale, million year, and much shorter time scale potential forcings on the climate system. And then generally speaking, the climate system will respond on shorter time scales. And We have records to suggest, right, like how the biology was responding to environmental change, but it's actually really, really hard with that absolute geochronology to actually say how quickly those eruptions were happening. So just to give an example, lots of people have pointed to Deccan traps and said, well, maybe there were sulfur aerosols that were being generated that caused global scale climate change. Well, the problem is these sulfur aerosols have really, really short residence times in the atmosphere, on the order of tens to hundreds of years. So we're never going to see that using absolute geochronology. So what we've been working on is actually trying to use relative geochronology and get information about the duration of time between one lava flow and the next. So not how old is this lava flow absolutely, but how much time elapsed between when one lava flow erupted and the next one. We're using two different techniques to get at that. Secular variation recorded by paleomagnetic data. That's being led by my colleague. I'm not going to talk about that, but I'll tell you about what we're trying to do with cosmogenic helium-3. So to walk you through this, I'll sort of illustrate this with a photo. Here we are working in a quarry this past May, when we were finally able to go out and collect samples. This is a big pile of basalt, and the lighting in here isn't great to see it, but there's a flow boundary here. So there's a really nice flow top of one lava flow, and then that lava flow is buried by a really, really thick second basalt lava flow. This basalt flow is thick enough that when it gets in place over the original lava flow, it completely shuts off the production of cosmogenic helium-3. Because if you remember, we're only seeing production of helium-3 in the uppermost few meters of the Earth's surface. So if I stick something that's more than 12 meters thick on top, I effectively shut off that production at this surface here. And just to give you a sense of scale, that's about 1 meter, and Raymond is probably, I don't know, like 1.5 meters tall. I think that's actually 1.5. Right, so like this is much, much thicker than that. And so for this work, we are looking at minerals in these flow tops from these now exposed, they're exposed today, lava flows. And we're looking at two minerals that retain their cosmogenic helium, pyroxene and ilmenite. And the idea is if we can measure that amount of fossil cosmogenic helium that's present in these flow tops, we can say how long that flow was exposed before it got buried by the next one. And we only did this field work in May 2022. Isolating these minerals is really hard because we need gram quantities from these admittedly quite altered basalts. So getting those samples separated is taking a long time. But this is where we're hoping to go. This is a plot of depth from the flow top to cosmogenic helium concentration. And these are model calculations. But our goal here is not to say this flow was exposed for 6,542 years before it was buried. We're not aiming for that level of precision, but we do want to be able to say, was this flow exposed at the surface for only 1,000 years? Or was it exposed for 10,000 years or 50,000 years before it got buried? And we should be able to resolve these order of magnitude questions using the measurements that we are planning to make. So I'll say stay tuned for that. But because of the pandemic, we didn't get to do fieldwork until May of this past year. We needed to do something in the meantime. And so what we started thinking about is how different were cosmogenic nuclide production rates in the Cretaceous? We're talking about 66 million years ago. And this is an important question to ask because the flux of cosmic ray particles that reach the Earth's surface or that even enter our atmosphere is heavily modulated by Earth's geomagnetic field. So here's a supernova generating these cosmic ray particles. Those particles have to have a much higher energy to enter the Earth's magnetic field at the geomagnetic equator than they do at the magnetic poles. And on these long time scales, we know that cosmogenic nuclide production rates have changed. We know this because the Earth's magnetic field strength has changed over geologic time, And also where India is sitting today, where we collected those rocks, is not where it was sitting in terms of paleolatitude 66 million years ago. And so we need to account for both of these things. We typically do account for these things when we do studies with cosmogenic nuclides in the late Quaternary, but we literally ignore them on longer time scales. Anything beyond the late Quaternary, people use a fixed field strength and a fixed effect on the production rate. So this is work that's been led by my PhD student, Mo Meejum, who's in the third year of her PhD, and she'll also be leading those measurements of the Deccan Trap samples once she has enough minerals isolated. So what does this look like? We've essentially been trying to develop a deep time production rate model specifically for the cosmogenic noble gases. The radionuclides don't really matter because they're not preserved because of their short half-lives on these timescales. So we've gone and used some models of what the Earth's magnetic field has done over geologic time. This is a model that was published last year that we're now using in our production rate model. There's a lot going on here. This is just different timescale binnings of the model, so 55,000 years versus 250,000 years. And this is a zoom in on just the last 5,000 years. One interesting thing that comes out of these paleomagnetic models that are based on geologic data is that over big portions of the last 70 million years, the Earth's magnetic field strength has been lower than the present day. There are periods when it's been comparable to the present day, but there is this systematically lower field strength over these longer timescales. And that's actually good for us because that allows cosmogenic nuclide production rates to be systematically higher. If the field is less strong, lower energy cosmic ray particles can make it in to the field. And so this is good for the ultimate objective of what we're trying to do. So we've incorporated these changes in the strength of the magnetic field into models. And the other thing that we've incorporated is information on paleolatitude. So what I want to draw your eye to here is this is India in the sort of yellow to red colors over the last 140 million years. And you can track its paleolatitude through time following these yellow to red dots. It's changed a lot. And so what Mo has been able to calculate is over the last 70 million years, this is a scaling factor. So think of this as a value of 1 here would be, we say the production rate is the same as some reference value through time. A value of 0.65 would mean it's 65% of that reference production rate. And so she's shown here sort of what the canonical thing that people do thinking about cosmogenic nuclides on these timescales is to set a fixed field strength and paleolatitude versus how that scaling factor, how that production rate changes through geologic time if she accounts for both changes in the field strength and the change in paleolatitude. And it changes a lot, right? These are tens of % differences, which is pretty significant. And it's something that we need to account for. We're very lucky in that this little period right here is when the Deccan Traps are erupting at the Earth's surface. And so a relatively high production rate compared to most of the rest of the time that since they erupted. Okay, and so one question we wanted to ask, since we haven't been able to look at cosmogenic noble gases in the Deccan samples yet, is does this matter? Can we look at other people's data to say that this matters? And the answer is yes, it does have an effect. So this is an example. This is from a paper by Laura Evenstar in 2017, where they went and mapped out all of these different fan surfaces in the Atacama that they are diagnosing as having different ages. We could argue about the geomorphology interpretation of this, but they've mapped these as being different age surfaces. And then they've measured cosmogenic helium and pyroxene in boulders that are sitting on these surfaces. And what Mo demonstrated is that if you hold the field constant, which is what they did in their paper, versus if you allow the exposure age to be time varying using this new model that she's developed, particularly for these samples with long duration exposure ages, where we're getting significantly different exposure ages and younger ages than the authors of this paper originally interpreted. And so that's meaningful in terms of their geomorphic interpretation of what these surfaces are in the Atacama. So we are super, super close, I hope, being able to submit this work, which is great because then we can move on to actually generating those new cosmogenic noble gas data from the Deccan samples. So that's what I wanted to tell you about the Deccan traps. Are there any questions, or should I save them all for the end? I'm happy to answer questions now if people have them. Or I can just plow on. No? Okay. All right. Now I want to talk to you about snow cover change in the Alps. And actually the approach that I'm going to be using for this, thinking about the things that happen on 100-year timescales and things that happen on 100 million year timescales, it's based in the same fundamental principles. So let me first show you, though, an example of the types of data that I'm going to be talking about. So when people started measuring cosmogenic noble gases in terrestrial materials in the late 80s and early 90s, there were early observations that suggested that things like helium-3 and neon-21 were experiencing diffusive loss at surface temperatures from common minerals. So this is one of those early data sets. We're looking at beryllium-10 exposure age. This is in millions of years here on the x-axis, measured in the mineral quartz, versus the apparent exposure age, also in millions of years, measured using cosmogenic helium-3 in quartz from the exact same rock samples. And there's a one-to-one line here, so hopefully you can see that the cosmogenic helium-3 exposure ages, or apparent exposure ages, are systematically younger than the same measurements made using a different nuclide. So exposure ages meaning how long has this rock been sitting at the Earth's surface. And these rocks happen to be from Antarctica, which is a pretty cold place. And so if you want to use cosmogenic nuclide measurements to say how long something has been sitting at your surface, that's pretty undesirable behavior, admittedly. And so systems that exhibited this behavior were largely ignored for a long time. So those systems include helium-3 in quartz and neon-21 in feldspars. But we can use this information. I've decided to kind of skip over the math here. But what I want you to know is that if I understand the diffusion kinetics, let's just talk about helium and quartz. If I understand the diffusion kinetics of helium and quartz, meaning I know the relationship between helium diffusion rate and temperature, I can predict how the concentration of helium-3 will change for different thermal histories. So there are people in this department that do noble gas thermochronology. It is the exact same principle. We're just producing the thing that we're interested in, or the thing that's diffusing, via a different mechanism. It's being produced by cosmic ray bombardment rather than by radioactive decay. So let's look at an example. We're going to look at this exact same plotting space that we looked at before. So beryllium-10 exposure age on the x-axis and helium-3 exposure age on the y-axis. And if I know the diffusion kinetics, I know the relationship between diffusion rate and temperature for the system that I'm interested in, I can predict how the helium-3 concentration, or in this same thing, helium-3 exposure age, will evolve for different thermal histories. And this example is just, let's hold the temperature constant, right? At -40, -30, -20, -10, and 0 degrees C. And I'll just throw those data from Brooke et al. 1993 back on here for fun. I've made lots of assumptions here that I wouldn't make in a quantitative application. But actually, just making an assumption about constant temperature and something about the grain size and something about the kinetics of helium-3 diffusion in quartz, I'm getting temperatures that aren't crazy for Antarctica, right? We're looking at something between -20 and -40. That's actually a pretty reasonable surface temperature for the area where these samples were collected. And so this is the principle that we want to use, but now we want to be more quantitative about it and say, can we actually go to a place and learn something really interesting about the thermal histories of the rocks that are there? But before I take you to the Alps, I want to highlight two important things that we have to consider when we're doing this that are a little bit unusual. So one, I've already mentioned that cosmogenic nuclide production rates are depth dependent. So if we have some surface production rate represented by P naught here, that's going to decrease exponentially with depth below their surface. This is important because almost every surface on the Earth is eroding, even if it's eroding at a relatively slow rate. And this makes our production rates of these noble gases time dependent, which is a little bit hard to wrap your head around if you're used to thinking about noble gases produced by radioactive decay. But the production rates are time dependent, but we can account for that pretty readily. The other thing that is different about thinking about surface temperatures is the form of the thermal history at the temperatures that we care about. So when we're talking about rocks sitting at the Earth's surface, they experience temperature oscillations on diurnal, yearly, and longer timescales. And so if we have some periodic temperature function that looks like this, we can look at diffusivity for that same temperature function. And this diffusivity function looks a little bit different from the temperature function because diffusion rates have a nonlinear dependence on temperature. And this is really important because you might think, well, I'm interested in knowing what the mean temperature that some rock sitting at the surface has experienced over time is. But that is actually not what's going to be recorded by the cosmogenic noble gases. The cosmogenic noble gases are going to record the temperature that corresponds to the mean diffusivity, or mean D here. And that temperature is always going to be equal to or higher than the mean temperature. So I'll often refer to this as the effective temperature or the effective diffusion temperature, EDT. That EDT, that effective temperature, will always be higher than the mean, and that's a function of this nonlinear dependence on temperature. So keep that in mind. The temperatures that we get are these effective temperatures, not mean temperatures. But if we know the form of this thermal history, if we know something about the shape of this thermal history and the amplitude and the frequency, we can actually functionally relate the effective temperature to the mean. Okay, so I want to take you to the Alps now. And snow cover is changing in the Alps, and that's true not only for the Alps, but for most mountain ranges all over the world. So here are just two photographs taken not quite 100 years apart of the same areas in the Alps. And if I circle here the same parts of the landscape, you can see that there's much more snow back in 1921 than there is in the modern. And okay, why am I telling you about snow? Well, snow is really, really effective at modulating ground surface temperatures. So these are data from the Alps in an area very close to our study area. You can see the air temperature in the gray here, and then ground temperatures in both red and blue. And the things that I want to highlight for you is that these periods where we lose the major temperature oscillations, the temperatures are at or below zero, the ground surface temperatures are periods when there's snow cover. So snow cover modulates the ground surface temperature. So why would we care if snow cover is changing? This is actually going to change the geomorphic processes that are operating in these places. So for example, it's going to change the amount of time we spend in this frost cracking window. I'm not going to explain this plot in detail, but whether or not we have frost cracking that's actually working to break these rocks apart or not, that's going to change if we change snow cover. We've seen, we're working on this project with the Swiss Avalanche Institute, where they think about rock falls too becoming more prevalent as you lose snow cover and rocks get heated up more during the summer months. And it's also really important for hydrology downstream of mountain ranges. So the snow that's melting in mountain ranges, and if that snow melt is changing systematically through time, has all of these downstream effects on ecology and also, on people. Right? We use the water from snow melt quite extensively, particularly here in the Southwest, which I'll mention a little bit at the end of this section. Okay, so we have been working with data from Goddard Pass. This is a formerly glaciated water divide in the Alps. So today it's the divide between the Rhine and the Po river systems. And we worked with 3 samples from Goddard Pass shown here at these locations. This is a photograph kind of looking up the hillside. So this number 6 is from the bottom of the pass, and then 11 and 10 are going up this slope. And so we measured cosmogenic helium-3 in quartz from these 3 samples and can compare that to the true exposure age that we know from measuring other nuclides that don't experience this leaky behavior. And this looks quite similar to those data I showed you from Antarctica. Everything plots below this 1-to-1 line, but we're looking at, this is now in years instead of millions of years. When we know the diffusion kinetics of helium-3 in quartz in these samples, we can convert this apparent helium-3 exposure age into a temperature that's integrated over that exposure history. So integrated over the last 10 to 15,000 years since ice retreated from this area. And so you can see this is the low elevation and high elevation sample, we observe a much higher integrated temperature than the mid-slope sample. The other thing that we did here is we put in instrumentation to measure what the modern ground surface temperatures are at these sites. So you can see actually pretty nicely here, everywhere where you see the wiggles go away are periods when there's snow cover. And then everywhere you see lots of wiggles is when there's no snow cover in these places. And so from these data, we're actually able to calculate what the effective ground surface temperature is today, or at least over the last several years. And so this is really useful because we can compare those temperatures that the helium records over the Holocene or since deglaciation to those present day temperatures. And what we find is that there's basically no difference for the high and the low elevation sample, but it looks like there's been significant temperature change for this mid-slope sample. And we think this is related to changing snow cover. So here's a nice ski map of the Swiss Alps. We have a great data set to work with here because the Swiss Institute for Snow and Avalanche Research has been monitoring things like ground surface temperature and snow cover, not in Goddard Pass where we're working, but in Gemstock, which is right next door. There's a lot going on in these plots. This is days under snow versus the effective temperature, snow water equivalent versus effective temperature. The key takeaway here is that we see effective temperatures increase as the time that we have snow cover decreases. So the less time that we're covered by snow, we're getting higher and higher effective temperatures. So we think that this data that we have here for this mid-slope suggests that this part of the landscape has experienced significant snow cover loss in recent time. But the question is, how recently? And we can actually constrain this. So using the observations that we have, both about the Holocene or the since deglaciation temperature, as well as the modern temperatures, and what we know about helium diffusion kinetics in these samples, we can constrain the response time. And so we've modeled this both using our helium observations, but we also have observations from OSL and other cosmogenic nuclides that support this, that all suggest that we see this significant change in snow cover here within the last 400 years. This could be associated with the start of the industrial period. That's kind of the flashy sell for trying to get this published. It could also be associated with the end of the Little Ice Age, or it could be both. But this is really cool because this is going far beyond our instrumental record in terms of telling us when snow cover began changing here. And so we're trying to do this closer to home and work in the Rocky Mountains in the Colorado River watershed. And the reason for this is that basically all of our in situ records from the Colorado River watershed show that snowpack has been declining over the entire record. So we can't say when that decline started to happen. And so we're going to try and use cosmogenic noble gases to look at that beyond the instrumental record. And so we've got some pilot samples from 2 locations in the Colorado River headwaters. And this is also field work that happened this summer. Here's Emily, ASU alum, working hard to get a sample. She and this PhD student from Yale, Griffin Goss, will be working on this together. Okay, I think I have enough time to tell you about the moon. And all right, let me tell you a little bit about lunar surface temperatures. And this is also using cosmogenic noble gases to look at past temperatures. But we're going to go way back in time now. Does anybody know what the name of this sample is? I bet Larry does. No? Okay. This is 76535. So it was collected at the Apollo 17 site. It is, without a doubt, the most interesting sample ever returned from the moon. And that might be true because a lot of people in the last few years have been working on 76535. It is interesting because some people think it is from the deep lunar crust. Some people think it formed at the base of an impact melt sheet. Some people think it came from South Pole Aitken. The hypotheses about this rock are like all over the map right now. And I got involved with thinking about its magnetic history, but really I wasn't thinking about that. I happen to know that we had pieces of plagioclase from 76535 in the lab where I did my PhD. And I said, well, what if we looked at cosmogenic neon in plagioclase? Because this is another system that exhibits leaky behavior. 76535 has an exposure age of 142 million years. Now that's coming from argon, which is also a stable isotope. So we don't know when that entire 142 million years happened, but the total exposure is 142 million years. So what did we do? We did diffusion experiments, quantifying the kinetics of neon diffusion in plagioclase from 76535. There's a bunch of points down here where there's basically no gas, but there's actually a nice, pretty clear relationship. This is a plotting space of inverse temperature versus the log of diffusivity. In this plotting space, we expect things to plot on a line, which they do pretty nicely here, which is good. And then we also measured the naturally occurring neon isotopes present in this sample. Neon is a little bit complicated because there are sources other than cosmic ray bombardment that can impart neon into samples on the moon. Specifically, we can have contributions from solar wind. And so this is a neon 3 isotope plot where we're looking at neon 21 versus 22, and then neon 20 versus 22. The key here is that almost all of these data plot on a mixing line between solar wind neon and cosmogenic neon. And so we were able to deconvolve this and basically take that solar wind component out. And so using the diffusion kinetics that we measured and these cosmogenic neon measurements, we were able to calculate an effective temperature on the lunar surface for this sample. And we get a weighted mean effective temperature of about 75 degrees Celsius. And that's actually really good in good agreement with other people who have used other isotopes to measure the effective temperature and also measurements made at the Apollo landing site. Now, hopefully you're saying to yourself, what, 75 degrees? That's like really hot for the moon. And it is, but you have to remember how extreme the lunar diurnal cycle is. So we go from temperatures approaching 100 degrees Celsius during the lunar day to temperatures below minus 150 degrees Celsius during the lunar night. So the average temperature on the moon is something like minus 70 or 80. But the effective temperature that corresponds to that mean diffusivity is something much closer to 70 or 80 degrees Celsius. And so these neon measurements made a lot of sense, but this is also kind of boring. because we don't anticipate that the moon had significant temperature variations in the last 142 million years, or if that exposure was sort of chopped up through time to a cumulative amount of 142. But we do anticipate that Martian surface temperatures have changed on these really, really long timescales. And so I thought it was pretty cool. There was a white paper that came out about like all of the potential things that we could do with sample return from Mars 2020. And one of the things that was talked about was looking at cosmogenic noble gases to try and think about past surface temperatures. And so, yeah, the moon is a little bit boring from this perspective, but maybe we can do it on other planetary bodies. Okay, that's all I wanted to share with you today. We walked through these three very different examples of applications of cosmogenic noble gases. I think they're really exciting because we can work on really diverse problems using essentially the same tool. And I'll end by thanking the people who have collaborated with on this and also our funding sources.
Students from the room, buddy? Over here, over here. You'll have to ask in a microphone because we do have people online to hear the question.
Okay, great, lovely talk. Thank you, Marissa. So my question would be, when you're analyzing, kind of trying to look at the helium-3 versus other cosmogenic isotopes, can you measure like helium-3 first and then measure like beryllium-10 in similar grains, or how do you work that out?
Oh, that's a good question. We're typically measuring them in separate aliquots. There's no reason why we couldn't. The only caveat is that we actually need a lot less material to do the helium measurement than we need to do beryllium. And so you would have to like aggregate a bunch of material from the helium measurements to make the beryllium measurement. Helium degasses at pretty low temperatures in quartz, and so I would be pretty confident that we're not volatilizing something like beryllium, but I don't know that for sure. Yeah, that's a great question.
Is everything kind of homogeneous then, that's not really a worry that you'd be doing it on?
Yeah, I mean, we're measuring beryllium and helium in like a sample of like this size. So it's quartz from the same rock, it's just a different aliquot. Yeah.
I'll do one from online while we're moving the microphone. Why are pyroxene and ilmenite specifically retentive to cosmogenic helium-3? Is it their structure? And this is from the first half of your talk, I guess.
Yeah, that is a great question. We think it probably has to do with their structure. That's largely coming from empirical evidence from diffusion experiments. We're actually going to redo diffusion experiments on those phases anyways, because there are no experiments for ilmenite, but ilmenite is isostructural with hematite, which we do have experiments for, and so we're assuming the kinetics are similar, but we need to do that experiment. And for pyroxene, there's only 2 experiments in the literature, and they give you wildly different answers. And you can imagine that different pyroxenes would have different diffusion kinetics. So we're going to do those experiments as well. We've irradiated the materials. We have the irradiation back now, so we can do those experiments. Yeah, I should mention, to do diffusion experiments, I didn't talk about this in this talk, but we irradiate samples with protons, and that generates helium-3 and neon-21 through the same nuclear reactions as cosmogenic nuclides, but we can get much, much higher concentrations doing that in a lab.
I'm curious about your Deccan project. How are you choosing your targets, your contact targets? Have you done that, and what do they look like?
Yeah, so there are lots of lava flows in the Deccan traps that are not good for this, which we learned, or I learned at least. My collaborators on this are people who have worked in the Deccan traps for a while. And so we're looking at places where we have pretty clear evidence that we're preserving most of the flow top, which is important for thinking about that depth constraint. So that's one of the primary criteria. The other criteria that, we may be biasing our results by doing this, but it's just something that we have to do, In places where we don't have a thick flow on top, but in places where we have maybe only a meter or 2 meter thick flow, that doesn't shut off production in the underlying flow. And so we've avoided places that don't have a thick flow on top. And so, yeah, I would say of the places that we went to, we sampled maybe less than 50% of them for cosmogenic noble gases. The other part of this project, which is looking at secular variation of the magnetic field, we can sample everything. And in fact, those short or thin flows are really, really good for using that approach to get at relative timescales. And so in those cases, that's going to be the better part of this project for looking at those types of flows. Yeah, does that answer your question?
Yeah, and then we worked a little bit in the Deccan on looking at the physical emplacement of lava flows, and so there's this idea that they're not just viscous gravity currents, but rather they grow by inflation.
Mm-hmm.
So they thicken by inflation. And so it'd be kind of interesting to know if you could see any of that, the time scale of that thickening by inflation in any of the work you're doing. I'm not sure how that would tie in terms of timescales.
I think
But
that
I'm interested.
that thickening is probably happening over like hundreds of years. Is that fair?
Yeah, I could see that being reasonable. Yeah.
And so in terms of, we do have like a lower limit of what we'll be able to do with the cosmogenic noble gases. We're not going to be able to look at things that are shorter than about 1,000 years of exposure. And so that might affect the depth systematics, but if the exposure duration is long relative to the inflation timescale, it should be okay, I would think. Yeah, that's a good question.
Get to mini Nicks, but I have one from online. Samantha, in the beginning slides, you mentioned magnetic waves where you compare two different figures. I was wondering why you believe this decreased.
Oh, here, why I say it's systematically lower.
Yeah,
Yeah, so okay. Part of this comes with like spending way too much time looking at these models in gory detail and also looking at the paleo intensity data that informs these models. And so if it's hard to see here, but the field strength here in the last 5 million years, there's lots of periods in the period before the last 5 million years when the field is less strong than it is sort of in the present day. And it's actually the strongest in the last, within the last few tens of thousands of years. There are periods in the geologic past where it is comparable or even higher than today, but we see lots of periods of low intensity going back in geologic time. I think it's harder to see in these figures than if you were to look at the paleo intensity data that are kind of informing these models. We by and large see systematically lower field strengths from the data. Yeah.
Was there a question back there? Go ahead.
Hi, Marissa. I had a question on basically doing the relative dating with the helium-3. I was wondering if there's any, or how you might deal with like any primordial helium-3 that's mantle derived that's coming up with the melt.
Yeah, I love it because yeah, this is a problem that we have to deal with. Although I think it's like one of our smaller problems. So there are two things that we can do. We can crush the samples in vacuum before we heat them up and use the helium isotopic ratio to correct for non-cosmogenic helium-3. And this is a pretty standard practice. It's kind of annoying to do because crushing, I don't know if anybody's done it, but it's just a pain in the butt. And it's very slow. It slows down the process by like an order of magnitude. We're trying to be tricky here and say, well, these flows are really thick. And so if I have one flow and I can see 15 meters below the flow top, I know there was never cosmogenic helium produced 15 meters below the flow top. So I can just use that deep sample to correct for the non-cosmogenic helium-3. So we're going to try and do that too. The other thing that we have to correct for, which I think is a relatively minor thing, is that these samples are exposed today. There's present day helium being produced in these samples. We went to places like that quarry. That quarry was not exposed until like 2 years ago. So pretty minimal present day production. A lot of our other samples are along road cuts. but we know the date that the road cut was excavated, and so we can correct for the very, very small present day cosmogenic helium. But yeah, that's a good question. So crushing and then also deep shielded samples are how we're dealing with that.
Thanks.
So I had actually, this is kind of a useful plot to show here, but these models that you're showing here, they seem to have an error envelope sort of
Mhm.
associated with them. So most calculations that you showed, I think a couple of slides later,
She's not using them. Yeah.
so what are the sort of systematic uncertainties and things that, you know, how certain is that curve that's calculated?
Yeah, so this curve is coming from a model that was published last year that's called McAdam. They actually looked at the field intensity over the last, I think it was 2 billion years. They have a model for this. And so they're using a bunch of paleo intensity data. So paleo intensity is measurements of things that tell us how strong the field was, like when that lava flow was in place, for example. And we can get paleo intensity data from Deccan directly. You're right, there is a lot of uncertainty in this curve. And presently, we're not propagating that into the production rate calculations. And that is not great. But I'll highlight what everybody does currently, which is kind of hold it constant. And I think that because we know that there's this systematically lower field, holding it constant at present day is like probably not the best thing to do. The other thing that I'll emphasize is that like for Deccan, we're not looking at a really long swath of time here in the geomagnetic models. We're actually looking at a very, very short period of time. And so when we're thinking about paleo exposure, so things that were exposed and then buried and no longer exposed, we can incorporate these uncertainties in the geomagnetic models much better. And so, yeah, that's a good question. And we're not dealing with it currently very well. But I think that we're doing better than what people have done in the past. These calculations, if anybody's run exposure age calculations before, they can be very, very computationally intensive. So there's also this trade-off in terms of like incorporating better uncertainty estimates and having the models not need a supercomputer to run. But yeah, good.
Anybody else in the room?
I had one more quick question along those lines. With the variation in field strength, does that come back in? How does that come back into when you're trying to then calculate surface temperatures? Is that something that then goes back into that calculation as well?
So for surface temperatures, we have an easier problem because we're only, in that example, we're only looking at the last like 10 to 15,000 years. And we do have geomagnetic models that are informing sort of our standard production rate calculators over those timescales. It's a good question. I think it's a little bit buried in those calculators how the uncertainty in those field models is actually being incorporated. And I think that it's probably not being done as well as it could be. But on those shorter timescales, we have much less variation as well. So like the last 15,000 years, yeah, the field has varied a bit, but it hasn't varied an enormous amount. And then on the moon, we don't have to worry about it. I'm just going to say we don't have to worry about it. We don't think the exposure that we're measuring comes from when the moon had a significant field. So.
Thank you. There are no more online. I have a comment though from me is would you take a big hello back to Emily Appel? She was actually a worker in our outreach program.
Oh, in the
years.
planetarium, right?
Yep,
Yeah,
absolutely. Yeah. And we loved her. So tell her hello.
I did not tell her. Here, I'll play it again just because it's fun. She is quite embarrassed about this video.
She was always a snappy dresser too. Look at how she's like.
Yeah, that is a pretty.
Everything is clean and.
she was really angry at this. There was this like vein, and she was determined to get this like nice big chunk of quartz-rich material out. Yeah, I will definitely say hi from
Thank you.
everybody, but you in particular.
Thank you very much. And thank you.
Thanks.
Thanks.